In the vastness of the cosmic ocean, a lone spacecraft, smaller than a family car, continues to drift farther from Earth than almost any other human-made object. This is Voyager 2, one of NASA's most ambitious and long-lived explorers. In late 2018, after more than 4 decades of travel, it crossed a milestone few believed possible when it launched in 1977. It became the second spacecraft to enter interstellar space. Now, having reached nearly half a century of travel, it has started sending messages from beyond the protective veil of the Sun. Voyager 2's flight is nothing less than remarkable. Initially envisioned in the era of the space race, the mission formed against the background of Cold War rivalry, computing power exploding at an unprecedented rate, and man's earliest explorations of the outer solar system. The 1970s were an optimistic time in planetary science. The Mariner and Pioneer missions had already demonstrated that the planets at the far reaches of the solar system were within grasp, but nothing on the Voyager scale had ever been tried. Voyager 2 was one of the Grand Tour missions, a mission designed to visit several outer planets via gravity assists by NASA. This kind of opportunity arises only once in 176 years, when Jupiter, Saturn, Uranus, and Neptune are positioned in such a manner that a single spacecraft can visit them in turn. It was launched on August 20, 1977, only 16 days ahead of its twin Voyager 1. The spacecraft was built for this once-in-a-lifetime alignment. These gravity slingshots were not just smart navigation, they were necessary. By exploiting the gravity of each planet to propel itself ahead, Voyager 2 could accelerate without expending additional fuel, taking it farther out to the edge of the solar system and beyond. Engineers calculated each path meticulously, aware that a slight error near Jupiter would mean missing Neptune by millions of miles a decade later. Voyager 2's flybys became landmarks in planetary exploration. At Jupiter in 1979, it took close-up images of the Great Red Spot, mapped volcanic activity on Io, and uncovered a complex ring system for the gas giant. Saturn in 1981 saw the spacecraft studying complex ring formations and returning data on Titan's thick atmosphere. Then there were the extraordinary feats. Voyager 2 is the sole spacecraft to have visited Uranus and Neptune. In 1986, it exposed Uranus as a pale blue-green globe tilted dramatically on its axis, with thin rings and eccentric magnetic fields. In 1989, its flyby of Neptune presented the solar system's fastest winds, more than 1,200 miles per hour, and disclosed Triton's geysers of nitrogen. These findings radically transformed our knowledge of the outer planets and their moons. But whereas these flybys garnered worldwide headlines, the Voyager crew always kept a higher purpose in mind: keep moving. The spacecraft did more than carry cameras and spectrometers. It also bore instruments to analyze plasma waves, magnetic fields, and cosmic rays, tools that would prove vital decades later. This longer-range mission was focused directly on the heliopause, that invisible edge where the Sun's influence surrenders to the interstellar medium. The Sun continuously produces solar wind, a flow of charged particles that creates a huge bubble in space known as the heliosphere. Within this bubble, planets are protected from much of the galaxy's radiation. Outside, cosmic rays run amok. The heliopause is the boundary where solar wind pressure equals that of the thin interstellar gas and plasma beyond. Scientists previously had argued about whether the boundary was diffuse or well-defined. Voyager 1 crossed in 2012 and provided the first direct measurements, but its plasma instrument had failed years before, so some answers remained open. Voyager 2, still operational in that aspect, would fill in the details. When Voyager 2 approached the heliopause in 2018, its sensors detected unmistakable indicators of transition. Cosmic ray fluxes from outside the solar system gradually increased. The solar wind slowed, then vanished. plasma density measurements spiked precipitously almost 20 times higher, verifying the spacecraft's entry into interstellar space. The direction of the magnetic field, unexpectedly, varied less than anticipated, consistent with Voyager 1's discovery and implying that the magnetic field of the Sun is more enmeshed with the galactic field than models estimated. A comparison of the two crossings showed that the heliopause was not a smooth shell, but a creased, dynamic boundary continually remodeled by solar activity and the ambient medium. Outside the boundary, Voyager 2's plasma wave instrument picked up faint, low-pitched oscillations, the hum of interstellar space. The waves are believed to originate from distant shock fronts, possibly from supernovae that date back billions of years. By measuring their pitch and frequency, scientists can calculate plasma density and learn more about the turbulence of the interstellar medium. The spacecraft's rapid passage through the heliosheath, the turbulent zone just inside the heliopause, was another surprise. Instead of a slow, uniform transition, Voyager 2 crossed a chaotic region filled with eddies and magnetic bubbles. This turbulence may be a key pathway for cosmic rays to slip past the Sun's defenses into the inner solar system. One profound revelation from both Voyager crossings is that the heliopause moves. Driven by the Sun's 11-year cycle of magnetic activity, it expands outward during solar maximum and contracts inward during quiet periods. This means that cosmic radiation exposure in the solar system varies over time, something that could matter for long-duration human missions to Mars or beyond. And now, in the interstellar medium, Voyager 2 is probing an area few imagined within our lifetimes. Galactic cosmic rays come unfiltered. The environment is surprisingly silent in radio emissions, suggesting a local void of low-density plasma. Measurements here might assist in mapping the Sun's trajectory through the Milky Way, disclosing whether we are approaching denser or less dense areas of interstellar space. Voyager 2 has also given us information about the tail of the solar system, a wake behind it formed by the Sun's motion through the galaxy. The spacecraft tells us the tail is distorted and filled with magnetic bubbles, remains of previous solar outbursts, hundreds of light years behind us. All from a spacecraft sent up when Jimmy Carter was president and personal computers were a new fad. More than 12 billion miles away, Voyager 2's weak signal, sent at a mere 20 watts, takes more than 17 hours to reach Earth. The data rate is slower even than early 1990s dial-up internet. Its energy is derived from a radioisotope thermoelectric generator, RTG, which generates slightly less electricity annually. Engineers at NASA have been shutting down heaters and non-essential systems to prolong the life of the mission. Even the science instruments will fall silent by the mid-2030s, although the spacecraft itself will keep coasting across the galaxy for billions of years. The Voyager 2 also contains a time capsule of Earth, the Golden Record, a gold-plated copper phonograph record containing sounds and images of our planet. Included are greetings spoken in 55 languages, the music of Bach to Chuck Berry, the sounds of nature, thunder, waves, birds, along with a pictorial instruction guide to how to decipher the record. It's a hopeful gesture, acknowledging that while the odds of it being found by another civilization are minuscule, the act of sending it says something profound about humanity's desire to connect. The Voyager 2 science is anything but abstract. What it teaches us about how the heliosphere protects us from cosmic radiation affects astronaut safety, spacecraft design, and even our knowledge of Earth's climatic past. And it puts our position in the galaxy into perspective. The solar system is not a hermetically sealed bubble, but a vessel navigating an ever-shifting cosmic sea. Voyager 2 continues to chart the interstellar medium, each piece of information contributing to our knowledge of the neighborhood galaxy. In a sense, it is humanity's first working starship, clumsy by science fiction criteria, but actual and already en route. Even when it goes quiet, its trajectory will pave the way for future probes. and Voyager 2 sails on, a solitary scout on the galactic oceans. It has shown us that the heliopause is not a solid wall but a living, dynamic border, a zone where the energies of our sun and the rest of the galaxy converge in a never-ending dance. Out there lies the vast unknown, full of secrets waiting to be unraveled. Many years after its transmitters fall silent, Voyager 2 will remain out there, a tiny, quiet observer of the history of our star and the endless space beyond.